Okay, everybody. Afternoon again. Evening, even. Yeah. To start us off, any questions or queries about anything at all? Yeah. You started it, good, yeah. So remember, coursework due on Wednesday the 7th. February, yeah.
Oh my God, I can't even imagine.
So 2 weeks from tomorrow. 2 weeks from tomorrow. So any other queries at the moment? Okay. There's me. Okay, so where are we? We're in chapter 7, Polynomial Congruences 2. So just a reminder of what we did yesterday morning. Yesterday morning, we proved Lagrange's theorem. Okay? Which was the best we can do at mimicking the fundamental theorem of algebra. Remember that the fundamental theorem of algebra says a polynomial of degree n with real or complex coefficients has precisely n solutions in the complex numbers. When you count solutions together with their multiplicities, the solutions of a polynomial can occur with multiplicity greater than 1. If the factor x minus the solution is a multiple factor of the polynomial. Okay? So you're familiar with the idea of roots occurring with multiplicities. Okay? Now, such a thing is not true of polynomial congruences. Okay? We've already seen examples of polynomials which have no solutions at all, polynomial congruences which have no solutions at all, and polynomial congruences which have more solutions than the degree of the polynomial. Okay? So we can't expect any exact relationship like the fundamental theorem of algebra. But what we do have is Lagrange's theorem, which we proved yesterday morning, which just applies in the case where the modulus is a prime. So when the modulus is a prime number, the degree of the polynomial gives you an upper bound on the number of solutions that the polynomial has. Okay? So a polynomial of degree n will have at most n solutions. Okay? It may have less, may have none at all, or it may have exactly n. Okay? And that was quite a nice substantial proof by induction, with quite a nice proof by contradiction in the middle of it, by showing that a bad polynomial of a certain degree, one that has too many solutions, implies the existence of a bad polynomial of a lesser degree, of the degree one before that. So that allowed us to construct an induction proof for this for all polynomials. Okay, so what we're going to look at today, having got that nice result out of the way, we're going to now consider the general problem. So we'll go forward to what page is that? Page 51. Page 51 in the notes, to look at the general procedure for solving a polynomial congruence. Okay? And I've indicated this before in some of the lectures, but this just sets out the steps we're going to follow for what the procedure is for solving a general polynomial congruence, and it's going to isolate and highlight the one remaining result that we need. And that's what we're going to consider in this session. Okay? So a general polynomial congruence is going to be something of this form, at the top of the screen. F of x congruent to 0 mod n, where f is a polynomial with integer coefficients. Okay? Now the whole procedure is based on the prime factorization of the modulus. Okay? So your modulus n will factor into a product of primes like this. Okay? So there'll be r primes, p1, p2, up to pr, r primes that divide n, and they will appear to various powers ai in the factorization of n. So that single congruence at the top is going to split into a set of r subcongruences, okay, where we consider the polynomial congruent to 0 modulo each of the prime powers from the prime factorization of n. So we've gone from a single congruence to a system of simultaneous congruences. Okay? R of them, and they've each got a different modulus. But you'll notice that each of the primes pi are distinct up here. Okay, they're different primes, p1, p2, up to pr. None of them are the same. So the different prime powers, what we can say is that the different moduli here in the system down here, that they're pairwise co-prime. Okay, that they're pairwise co-prime. So when you've got a system of simultaneous congruences with pairwise co-prime moduli, that means the Chinese remainder theorem will apply. Okay. Chinese remainder theorem will apply. So if we can solve each of these, okay, if we can obtain solutions to each of these subcongruences, then those sets of solutions, you then got sets of solution, one for each value of I. Those sets of solutions can be put together using the Chinese remainder theorem to find corresponding solutions to the original problem. Okay? So remember, the Chinese remainder theorem takes. There's a bit too much chatter filling the class. Thank you.
Chinese remainder talked about.
The Chinese remainder theorem talked about a set of congruence classes, moduli, a set of different moduli, which were pairwise co-prime. An example of a set of moduli that are pairwise co-prime are this set of prime powers. Okay, so the primes are different. So once we've solved all of these problems here, we'll be able to take a selection of the solutions. So one solution from each one, and then apply the Chinese remainder theorem. The Chinese remainder theorem will give us a unique congruence class modulo the product of all the prime powers, i.e. modulo the original modulus n. That will be a single unique, one of the unique solutions of the original congruence. Then if you vary the set of solutions, you take a different combination of the solutions from these, and apply the Chinese remainder theorem again, you get another solution to the original congruence. So once we have the ability to solve the congruences like in part 2 there, we can apply the Chinese remainder theorem to put the sets of solutions together to obtain solutions to the original congruence. Okay. I also outlined that procedure in a couple of lectures, I think at the time that we introduced the Chinese remainder. So what this shows for us is that we need the ability to solve congruences like this. Okay? And this is what we're going to describe now. There's an algorithm for finding the solutions of these congruences. And it's based on what we call a solution lifting technique. So now we're fixing our attention on polynomial congruences of this form. Polynomial congruences where the modulus is a prime power of a prime. Yeah. What we're going to describe as a lifting procedure. So a procedure that takes solutions to the congruence modulo p to the k minus 1. There's still quite a lot of chatter. These rooms are designed for the audio to go everywhere. Thank you. We're going to describe solution lifting. This algorithm, which we'll describe, will take solutions to the congruence modulo p to the k minus 1 and associate them, lift them to associated solutions to the same congruence modulo the next highest power of the prime. So if we've got solutions to an earlier power, we can lift them, link them to, construct solutions to a later power, p to the k. So this will describe, this lifting procedure will give us a kind of an inductive process. So we can start by solving, if we want to find solutions to this, we can start by solving it mod p, the lowest power of the prime. Start by solving it mod p, and then use the lifting procedure to lift those solutions to solutions modulo p squared. And then use the lifting procedure again to lift those solutions to modulo p cubed, and lift those to p4. You keep on lifting your solutions up and up the ladder until you reach whatever the desired power of p is. Okay. So what this theorem describes is the lifting procedure. How to take solutions to the thing modulo 1 power of p and lift them to solutions modulo the next power. So here it is, theorem 7.2. Now we're not going to prove this theorem. We're going to just leave out the proof of this, but we do want to understand how the result works and be able to apply it, okay? Now it's laid out as an algorithm, and there are two decisions to make. There's an outer decision, which is the round bullet points, and then within the second decision, so there's two answers to the first question, and within the second answer, there is a further question which has two bullet point answers. So you either end up here or you end up here. So it's a decision procedure which describes an algorithm. Okay. So this is what we're starting with. We're starting with the assumption that we have a solution R to this polynomial congruence modulo p to the a minus 1. Okay, that's the assumption that we start with. Okay. And what the theorem is going to describe is, can we associate to R a solution to the thing, to the congruence modulo p to the a? So we're starting from the fact that R is a solution to it modulo p to the a minus 1. So the first question is a question about the derivative of the polynomial. Okay? So we work out the derivative of the polynomial, and we evaluate the derivative at R. And then the question is just on the status of that value, f prime of R modulo p. So we test it. And that value will either be congruent to 0 mod p down here, or it won't. Okay? It's a simple decision to make, an inspection, and you make the decision. Either it is congruent to 0 or it isn't. The nicest case, the cleanest case is when it isn't congruent to 0. When it isn't congruent to 0, then the theorem says that our solution R lifts to a unique solution to the polynomial modulo p to the a. Okay? So your solution R at the level p to the a minus 1 lifts uniquely to a single solution at the level p to the a. And the new solution S is given by this expression here. It's built out of R t times p to the a minus 1. So p to the a minus 1 is the current modulus you're at. What is t? T is a solution to this associated congruence here, where we solve this congruence. T times this derivative value plus the original value f of R divided by p to the a minus 1, congruent to 0 mod p. Okay? But this congruence will have a unique solution modulo t. A unique solution because the f prime R will be non-zero mod p, so it will have an inverse modulo p. So we can multiply both sides by the inverse of this quantity to find the solution t. So that's in the case where f prime R is non-zero. In the case where f prime R is 0, then we ask ourselves a further question. Based on the value of f of R itself. And in this situation, the solution R is either going to not lift at all, it's either going to not generate any solutions, or it will generate multiple solutions at the next level. Okay? If the value of f of R is non-zero modulo p to the a, then the story stops. R does not generate any new solutions to the polynomial congruence at the level p to the a. Whereas if the value f of R is congruent to 0 modulo p to the a, then the solution R does lift and it splits. It generates multiple new solutions at the next level. And it will generate p different solutions given by this formula here. So you got these p values, S0 through SP minus 1, indexed by I goes from 0 to p minus 1. And they're all generated by R. They're all in the same congruence class of R modulo p to the a minus 1. But they're all the different representatives that there are of R in that congruence classes in that congruence class, but they'll be in different congruence classes modulo p to the a. So you add on to R all the multiples of p to the a minus 1, where the multiple index you're using goes through 0 through p minus 1. And this gives you p new solutions to the polynomial congruence at the next level up. At the next level, f of x congruent to 0 modulo p to the n. So it's laid out there. It seems a bit unfamiliar and technical when we first see it like this. But we'll work through an example now. So it'll be good for you to have that page open beside you because we'll be consulting it all the time. So this describes how to lift solutions one level. Okay? You query the value of the derivative at the solution. If it's non-zero, it lifts uniquely like this to give you a new solution S. If the derivative is 0 at the solution, you ask yourself a further question based on the value f of r. Depending on the answer, you either get no solutions or you get multiple solutions generated at the next level. Okay? So the best thing we can do at this stage is to jump in and see an example of this, operator. So the example we're going to use is example 7.1, which is at the bottom of the page. So keep page 50 open beside you. And we'll look at example 7.1. This is solution lifting our solutions. So the problem we want is to solve x squared plus 3x minus 16 congruent to 0 modulo 81. And 81 is, of course, 3 to the power 4. Yeah, 3 to the power 4. So that's the power of a prime. Okay, so the theorem applies. Okay. So our p is 3. The ultimate exponent we're going for is 4. But we want to build up to it level by level. Okay. So we begin by considering same polynomial congruent to 0 modulo 3. Okay, the first level, 3 to the power 1. Now, what do we think of that? Now, if we're considering the polynomial modulo 3, we should immediately query the different parts of it and see if they simplify modulo 3. I mean, in the original problem, they don't really simplify modulo 81. 3 and 16 are both less than 81. But when we're considering it modulo 3, there is a simpler representation of it we could use. In the x squared is still x squared, but the 3 times x, well, that's going to be 0, isn't it? You're considering it modulo 3, so multiplying it by 3 is the same as multiplying it by 0 when you're looking for solutions modulo 3. So the 3x part we can actually leave out. And 16, well, what is 16? 16 is congruent to 1 modulo 3. 15 plus 1. So this is actually minus 1. Okay. So what we were doing there is reducing the coefficients mod 3. So the polynomial looks a lot simpler now. X squared minus 1, congruent to 0. And what solutions does that have? Well, x squared congruent to 1. And x squared congruent to 1, you're tempted to say x is congruent to plus or minus 1. And you'd be right. Plus or minus 1 modulo 3. So that's the same as saying x is 1 or 2 mod 3. So there are two solutions. These two congruence classes modulo 3. Because there are only 3 congruence classes modulo 3, represented by 0, 1, and 2. And 2 of them are solutions to this polynomial. Okay. Substitute in either of those values, you'll see you get multiples of 3. You get 1 plus 3 is 4, minus 16 is minus 12, which is 0 mod 3. Put in 2, you get 4 plus 6, which is 10, minus 16, minus 6, which is again common to 0 mod 3, the multiple of 3. So it seems reasonable enough. Okay? So we've got two solutions sitting at the bottom level. So we've got this theorem now which allows us to lift solutions to the next level. The next level will be 3 squared, 9. So we'll take them one at a time. So we'll let r equals 1 and apply theorem 7.2. Okay, to lift r equals 1 to a solution, maybe, or solutions for the polynomial at the next level, which is f of x congruent to 0 modulo 9, 3 squared. So we look at the statement of the theorem, which you have to your front of you, hopefully. And the first decision is to query the value of f prime of r. Okay. So f prime of x, just to find the derivative of the polynomial, it's 2x plus 3. Okay. So f prime of r, when you evaluate it at the solution, so we're focusing on the solution 1. Well, that's 2 plus 3, which is equal to 5. But the decision we have to make is this 0 or non-zero modulo p, which is 3? Well, that's clearly non-zero modulo 3. 5 is not a multiple of 3. I'm going to 2 modulo 3 is the standard representative of it. So that puts us into the top bullet point. Okay. If f prime of r is non-zero. So by theorem 7.2, r equals 1 lifts to a unique solution S. And this S is given by r plus t to the p a minus 1. So this is equal to 1 plus t, whatever the t is, which we'll find at the moment, by p to the a minus 1. Well, that's by 3. And the prime p is 3. And the a minus 1 is the previous level that we had, which was the modulo 3. And the t, see the t is described to us, where t is the solution. T is the solution to t times f prime of r plus f of r e to the a minus 1 congruent to 0 modulo p. So what is that solution? That is t. So what f prime of r? Well, f prime of r we had was 2. I mean, it was 5, but a simpler representative of it is 2. F prime of 1. I'm sorry, that's my f prime of r. But I'm considering it modulo p, modulo 3, so I'll choose the simpler representative 2. F of r, so that's the original value, f of 1. So what was that? That was the minus 6, was yeah, 1 plus 4. 1 plus 3 is 4. Minus 16 is minus 12. So minus 12 was the value f of 1. But I divided by p to the a minus 1, which is the 3. So minus 12 divided by 3 is minus 4. So that's minus 4. This is congruent to 0 mod p. Well, that's the same as saying that 2t is congruent to plus 4. Oh, so the p is 3. Plus 4, but 4 is 1 mod 3. So I need to multiply both sides by the inverse of 2. The inverse of 2 modulo 3 is 2 itself. Because 2 times 2 is 4, which is congruent to 1 mod 3. So that's true if and only if t is congruent to 2 mod 3. Remember, 2 inverse is congruent to 2 mod 3. So the t is equal to 2. So what's my s? Go back to my s here. My s is 1 plus 2 times 3. So s is equal to 7. This is our lifted solution to the polynomial congruent to 0 modulo 9. If you want, you can test it. 7 squared, 49, plus 3 times 7, 21, gives us 70. 70 minus 16 is 54. And is 54 congruent to 0 modulo 9? Yes, it is. It's 9 times 6. So we haven't made any errors, I don't think. But now we're halfway there, so to speak. We've got a solution to our polynomial congruence modulo 9. The original request was for solutions to it modulo 81. So we go back now and apply the lifting procedure for a second time.
So how did you check it at the end?
So I checked it by, so the claim here is that it's a solution to the polynomial modulo 9. So I substituted in the value 7 for x, 49, 7 squared, 49 plus 21, 49 plus 21, 70. Minus 16 is 54, which is 0 mod 9. So it's a multiple of 9. 9 times 6. Okay. So now we lift again. Apply the theorem to the solution r equals 7 to lift it to solutions for f of x congruent to 0 mod 27. The next highest power of 3 after 9.
Apply theorem 7.2, didn't say?
Yeah, apply theorem 7.2 to this solution. R, I just call it R again, because that's what it's called in the theorem. Solution R equals 7 to lift our solution and try and find a solution to the polynomial congruent to 0 modulo 27. So again, we ask ourselves this first question: what is f prime of R? F prime of R. Well, f prime, the polynomial, the derivative is still 2x plus 3. And we evaluate that now at our solution set. So it's 2 times 7 plus 3 is what? 14 plus 3, which is 17. But the point about it is it's certainly congruent to 0 mod 3. If you look at that first round bullet point decision, the theorem, you have to assess that value, whether it's 0 or non-zero, modulo 3. So again, we've got something non-zero. So again, so R will lift uniquely. So a unique solution, S to f of x congruent to 0 mod 27. Given by the same formula, S is equal to R plus t times p to the a minus 1, except this time R is 7, and p to the a minus 1 is R9. Okay, because that was the previous level we were lifting from. And t is the solution to this. T is the solution to t times f prime r plus f of r over p to the a minus 1, which for us now is congruent to t times f prime of r. Well, I've already worked out f prime of r is 17, but I'll simplify it modulo 3. This is a polynomial modulo e that I'm going to solve. So what's 17 mod 3? It's 2. So it's t times 2. So this 17 is congruent to 2. So this 17 is going here, because it's f prime r. But because I'm only going to consider it modulo 3, I may as well reduce it as I'm going. To reduce it to 2. I then need the value f of r, so r is 7. The value f of r I worked out a minute ago, f of 7 was 54. So 54 divided by p to the a minus 1, so that's the level we're lifting from at this stage, so that's our 9. So it's 2 times t plus, well, 54 divided by 9 is 6, and I have to solve this congruent to 0 mod 3. But you see 6 is 0. So that's the same as saying 2 times t is congruent to 0 mod 3. 6 is 0, isn't it? Yeah, but that's just the same as saying t is 0 mod 3. So our solution is, so our this parameter t, or this value t in the solution S that we want is actually 0 this time. So that means we don't get that bit. So we've still got this solution 7. So it just happens to be the same integer, which is the standard representative. But it's a different thing. It's now representing a congruence class modulo 27. So S congruent to 7 modulo 27 is our lifted solution to f of x congruent to 0 mod 27. Remember, f of 7 came out to be 54. 54 is also a multiple of 27. It's 2 times 27. So that checks out. It's still a solution modulo 27. So we're one step away from our destination. Our destination was modulo 81. We've now got a solution to the thing modulo 27. So we just need to raise it to another multiple of 3. Any question about any of those calculations at the moment?
You said 6 is 0. Why 6 is 0?
Why is the t 0? Well, because it's the solution to 2 times t congruent to 0 mod 3. And there's only 3 candidate solutions, 0, 1, or 2. I mean, if it's 0, you get 0. If it's 1, 2t is 2. And if it's 2, 2 times t is 4, which is 1 mod 3. So the only solution is t congruent to 0. Yeah. I mean, I think you're complicating it. It's an equation. 2 times t is 0. You solve it by dividing across by 2, multiplying both sides by the inverse of 2. But when you multiply it by 0, you're going to get 0. So t is congruent to 0. So we got to lift one more time for this. So lift again. We're starting with a solution r equals 7 mod 27. And attempt to lift. We're attempting to lift it to f of x congruent to 0 modulo 81. So the same decision procedure. We evaluate f prime of r, which is f prime of 7, which we already have. It's 17, which is still congruent to 0 mod 3. So it lifts uniquely. So it lifts uniquely to a solution S, given by S is r plus t to the p a minus 1, and that's 7 plus t, but p to the a minus 1 is now 27, because that's the level we're lifting from. For t, t is the solution to this t times f prime of r. plus f of r divided by p to the a minus 1, which is t by z prime r is still 17, which is 2, because we're going to consider this thing modulo 3. So reduce the 17 to 2, as I did before. F of r, well, that's 7. F of r is still 54. But it's 54 divided by 27 now. That's the level we're lifting from. It's p to the a minus 1 at the bottom. So that's congruent to 2t. 54 divided by 27 is 2. Congruent to 0 mod 3. And that is solution t congruent to minus 1, or otherwise known as 2. That makes sense? I mean, you can take the minus 2, the plus 2 to the other side, it gets minus 2. The 2t is congruent to minus 2, so t is be congruent to minus 1. But minus 1, I mean, the standard representative we choose for it is 2. 2 modulo 3. So that's our value of t, which feeds back in there. So we finally have the solution S, which is 7 plus 2 times 27, 7 plus 54, which is 61, modulo 81, to the original problem, the original congruence. So I made that example a 1, 2. How many times we left? 3 times we left. Was it? Or 4 times? 3 times. We lifted it to 2, to 3, to 4. Yeah. But still, we left one solution behind at the bottom level, which was the solution r equals 2 to the original congruence modulo 3. So to complete the procedure, you really have to go all the way back down and drag that solution r equals 2. Drag it all the way up through the various levels to find out the solutions. Well, we might necessarily do that right now. I do want to show you a quick how to verify these solutions, how to obtain these solutions and verify them easily using CoCat, using Sage. And you might be able to do this stuff in MATLAB as well, but Sage is so much better set up for this. A really quick way for using Sage is to go to the Sage Cell server, which is Sage Cell at Sage Math. You've seen me link to that before with some things. And it's got a really, I think it's some kind of command, solve _ mod. Yeah, so I did the tab completion under that. So solve _ mod is the command. So Sage Cell is just this single input box that you can put some Sage code in to solve, and you'll get the output from it. It's probably also better to make use of it in the CoCalc environment as well. I'll show you that as well. Just while that's loading up, here's how to solve it. In here, so you type in the equation. So what was this equation? X squared plus 3 times x minus 16 congruent to 0. So equals 0. Remember, you represent the equality sign in computer languages typically with the double equal sign, and you just give it the modulus as the second argument, I think. And execute that. There's a big button there. You can do Shift Enter, I think. Yeah, the thing is spinning, and it's giving us, okay, there's loads of brackets everywhere, but it's just telling us that there's 2 solutions, 17 and 61. So 61 is the one we just found on paper. So we're seeing in advance now that probably, well, yeah, certainly the other solution, r equals 2, will lift to 17 eventually. You lifted up the 4 of the 4 sleeves.
25 minutes.
You are better off if you haven't done so already. I would encourage you to set up your own account on CoCalc. Basic accounts are free, and they have all the functionality that I was going to show you here. And if you create a basic, so the most immediate way you can make use of Sage and Python in here is just with the Sage worksheet interface here. So you can access the same command here. Again, I remembered it was solve mod or solve something. It's taking a while for the completions to load in when you first bring up the page. But I've typed the first part of the command solve. When you press tab, it gives you all the possible completions. So yeah, solve mod looks like the one for solving congruences. There's ones for Diophantine equations and inequalities and a general symbolic solver there. But solve mod is the one we want there. So we can call it using this kind of code, same kind of code. And evaluate using Shift Enter. It'll evaluate that and it gives us the same output. The other, I mean, you're in the fully featured Sage environment when you're using these worksheets on CodeCalc. Well, you can another useful thing is that when you discover relevant commands using tab completion and what you think some of the starting off of the command might be. But when you position the cursor just to the right of the opening bracket for the arguments, when you press tab, then it helpfully pops up the help screen for the command. And in there, well, you can see all the help, the explanation of what the command is, what its inputs do, and often, or always almost, there are some helpful examples here, illustrating typical ways to use the command. Okay? You can get some good. You can solve multivariable congruences. You can deal with congruences which are even have extremely large moduli. And some good examples there of also simultaneous congruences. So if we're working through the exercises, see in exercises 7.1, there are some good examples for you here to experiment with. All the moduli are always powers of primes. So you should get some practice using the theorem. I mean, I'll never insist that you remember it or anything. It is reproduced in the exam handout. If you ever did need to use this in the exam statement of the thing, the specification of the algorithm is given. But you need to be comfortable with using it and familiar with how to operate it. So you should use Sage to verify your solutions to any of these. It's a nice, quick way to obtain solutions. Okay. So any questions just about what we did there? That's all at this stage. Any questions about anything? Open season. Okay, well maybe we'll knock it on the head for this evening. 5:45, and I shall see you all later on. So we're ready now to. Next week we'll begin the final chapter on quadratic residues, which is loads of good stuff to come in that. Okay.
It sounds good.
Sounds wonderful.